Good morning, everybody. Hey, who's here? So we got Peter. Peter showed up early, and so did Chip Longflare, whose comment seems to have disappeared. Maybe he's not here anymore. Some Call It Fun, Chris, and Station 240, Michael, Gerald, Frank. Awesome. Yes, the intro video was breaking up. There are two things there. There is actually an intentional stutter in the audio at about, I think it's at about the -7 seconds mark. So there's a bit where it goes, that's in the original music, like the soundtrack. But I could actually see in OBS that I was dropping frames, so there's probably extra stuttering this time. So, just before I get into things, I just want to do a quick shout out to the Indigenous Literacy Foundation. And this is an organization that is attempting to bridge the educational divide and provide Indigenous kids with access to literacy education, which is a really cool thing. So, come on, respond. Yes. Okay. Now, I've got big plans for today. I've got ambitions of achieving yeah, right. We'll edit that out in post. Achieving 3 things. And I don't know if we're going to get there. Someone said, is this like a squirrel-free guarantee? And it definitely is not. They're going to be squirreled. So, Peter, YouTube thinks you deserve 144p resolution. Oh well. Hopefully it'll improve for you. Now, 3 things. The first. All right, before I get to the 3 things, let's start with the embarrassing thing. Right from the start of this project with the multimeter, I've had 2 methods in mind for interfacing with it, and ultimately what I want to do is have a device that's embedded within the multimeter. So you basically just pick the multimeter up, turn it on, and you've got Wi-Fi. And as an intermediate thing, I've been wanting to get data out of the optical interface. And a whole lot of what we've been doing over the last 2 months now is messing around with the data that comes out of that optical interface, looking at its PCB, looking at the schematic, and seeing what we can get out of it. And we have been seeing waveforms on that connection. Now, this is the really embarrassing bit. Let's have a look at, okay, so this is the piece of paper that I printed out. Oh look, my oscilloscope camera has twisted. It's just, it's hanging there on, anyway, it might have to do until I get a better setup. So this is the piece of paper that I printed out ages ago when we were looking at this little interface PCB. So this is the schematic of the PCB and the connector that plug into the back of the multimeter, picks up the optical signal through this photo transistor, and then does some wiggly switching stuff, and then sends the data out. Now, I was contacted actually a couple of weeks ago, and I was waiting until I got a chance to do a live stream about this particular thing to follow it up. And this is one thing I'm really bad at, is I have people messaging me and sending me stuff constantly, and I don't keep track of who it was. So someone who had worked on a UT61E project quite a while ago, like a couple of years ago I think, had taken the adapter. I don't have one here to wave in front of the camera because it's currently plugged into my multimeter over the bench. They'd taken the adapter, cut the serial connector off it, and wired it up with a MOSFET to do as an inverter, and connected it up. So, and they were getting data out of it. And what they discovered was when they started trying to read the data, they weren't getting anything. And so they started digging into what was going on, and discovered, this is the embarrassing thing, look at this. This is the DB9 header, and this is the data that comes from the little optical interface. It's labeled as TXD, and I've drawn an arrow on it here, so this was however many weeks ago that we were doing this. TXD and data coming out. So this pin here, pin 1, 2, 3 on the DB9 connector, is where we have been connecting our multimeter and seeing that waveform. Now, let's have a look. No, don't wake up. I've just got to mute my voice assistant. It just started flashing at me. So let's have a look at this. This is the file. It's the same thing as what we were just looking at with that hard copy, but it's in a better form here because it's the actual original. Now, this is the embarrassing thing. Let's open up a browser and do a search for RS232 pinout and see what we can find. Images. Well, it's it's interesting. Let's see. This one will do. And can I make this bigger? Come on, give me the pinout. Where is the image? There it is. So the numbers don't really matter that much, but, well, they do. Let's look at this. Where are we? Pin 3, transmit data. Let's zoom this way in. Transmit data. Somebody cross-transmit and receive. It's the classic thing. It is the pin that is labeled transmit on the connector, so it's pin 3, but that is where you transmit data out of the port, not where, anyway. So, pin 2 is receive data, and come on, spinning beach ball of death, move sideways, look at this. So what this schematic is showing, so what this shows basically is that this schematic is wrong. It is not reality. And when this was pointed out to me, I went digging and connected a multimeter. I'm not going to do it right now, I'll just tell you the results. I buzzed it out, and what happens is that the PCB that is in that little adapter has both transmit and receive connections. It's actually got the circuitry on it so that it's a full bidirectional transceiver, and the transmit side is not populated. The receive side is populated, and it is not shown, so the transmit side is not shown at all in this schematic. This schematic is not correct. It is not the original schematic for this device. It's someone's recreation of the circuit, and they got it wrong. And I trusted it. So I just looked at this and saw the label TXD, that's transmit data. So it's transmitting data from the thing. No, that pin is transmitting data from whatever is connected to this connector into this device. And it is the receive pin on this device. So, not only is the circuit incomplete because it doesn't have the actual transmit side of the circuit, but what is there is wrong. That line there, TXD, should be connected to pin 2. So I traced it through, and what happens is that where pin 3 actually goes, if you check through on the cable, it goes from the connector onto the PCB in that little adapter, onto pads where the transmit circuitry goes, but there's nothing there, it's not populated. So what we have been doing this whole time that we've had the multimeter on that device is we have been picking up voltage induced on a parallel wire because they're running side by side through the same cable. And that's it. There is actually, where this thing is here, so this pin 3, let's go back to the overhead. And I'm going to grab myself a pen, and it better be a red pen. It deserves to be a red pen. So what's right here, that is not the transmit line. What actually happens is this wire comes down here and it connects to pin 2, not pin 3. That is not there. And pin 3, it actually runs parallel to it, and then it goes in onto the PCB, and then there's other circuitry which isn't shown here at all. It's like there's a transistor and an infrared LED and some stuff, so that this data can be used to turn on a transmission LED, which is like the equivalent of this part of the circuit. But what we've been doing is this wire here, which is the actual outgoing data line, and this wire here on pin 3 runs side by side in that cable for maybe a meter or so, and the data that is being sent on this connection was being inductively coupled onto this wire that goes nowhere. So we were effectively using an antenna. We just had the multimeter, sorry, the oscilloscope input connected to a wire that was picking up the voltage from the wire that was right beside it. No wonder I couldn't get anything to work. No wonder it wouldn't switch a transistor, and no wonder we were seeing that decay in the signal over time. So the voltage would tend, the whole thing would shift down. So once I saw that, that was one of those, oh my God moments after all that. So the good thing is, once I change the pin, it all works. So we'll get to that. No, let's see. Okay, since I'm on this subject, I was going to do 3 things in a specific order. I'm going to mess that around now. In fact, I'm going to do number 2 and then number 3, and then we might get back to number 1 if there's time. All right, so number 2 was going to be connecting up to this and reading the data. So let's do that. I'm going to, what we'll do is open up Arduino. Now the thing is that we already had pretty much everything, like what we had should have worked way back at the start when we had the circuit with the transistor. Is it drawn there anywhere? Yes. Look at this. I'll switch back to, while I'm waiting for Arduino to open. Come on, switch. There we go. See this little circuit here, which I drew like way back right at the start, and we tried it and it didn't work, and that's because that data coming in on TXD was just the induced voltage, and it didn't have enough power to make this transistor turn on and off, so nothing happened. I'll slide this over here. Just got to move a few things. So this is the breadboard that we've had sitting here. It's been like 2 months now. This transistor that is down on here with these other things that we started off with using, all I did was I've changed the connection on this from pin 3 to pin 2. Oh, Arduino IDE has just finished opening. So what we've got here is the firmware that we've been messing around with on the live stream, and I've got it plugged in. Okay, let's get this set up, ready to go. Where'd it go? Oh, there. I had a signal generator sitting on top of it. So this is the end of the connector that goes to the optical interface, which goes to my multimeter, which is currently up attached to my bench. So if I plug this in to there and turn on the multimeter, in fact what I'll do is grab multimeter probes, and I was going to use a signal generator for something totally unrelated, but let's do this just so that we've got some data coming in. Wake up. Alright, so The frequency is too high for us to see anything useful, but anyway, we're going to get back to this function generator. We'll use it later once we're messing around with comparators. What I'm doing now is just connecting it to the multimeter. What have we got? Volt peak to peak. Oh, it doesn't matter. It's just making the numbers jump around. That's really all I want. I just want to have the numbers jumping so that we see something coming out of it. I'm just going to turn up the voltage because the frequency is so high. Anyway, that doesn't matter. That's not even relevant. All it's doing is providing something that goes into the multimeter. All right, so we've got the function generator providing a signal, which is going into the multimeter. The optical interface from the multimeter comes down here and it goes into the MOSFET circuit, which is this one on the piece of paper there, which goes into the ESP32. And then if we come back over here and open the serial monitor, let's see, and now we are getting data coming out of the multimeter. Hooray! And yes. Okay. All right, time for a pause. I'm going to stop for a second. So what you can see there's what I'm seeing on the multimeter that you can't see is the numbers that are jumping around are like 0.004445, 53, 49, and if you're watching the data in that's coming out of this, you'll see that last digit, the last two digits, matching. Basically, this is the data. It's undecoded, but even without decoding it, so there is the thing, the first digit is the decimal point offset, and then the rest of it up until the semicolon is the value. So this is a 0 offset from after the first digit. So if we ignore the first digit and then it's 0.004441 is what is on there, and that is what is on the screen of the multimeter. Amazing. Yes. So, what now? All right. So we have data coming off the multimeter with just one transistor. That's all we need. All it is an inverter that comes off that data line. Now, let's have a look. I'm going to see if we can get anything useful coming out of this. It's nice to be able to see things. Just give me a second while I hook stuff up. What have I got? I need a ground connection for the multimeter, and then I'm going to find the right pin, and I'm going to turn off channel 2 just temporarily, and I'm going to switch this around so that you can see what's going on. What do I want? I want the overhead view, which gives the oscilloscope, and get rid of the menu, and that angle is really horrible. But this is such a dodgy setup here with this little webcam that's pointing at the screen. All right, now you can just see little glitches happening there. And where's the, I'm gonna stick it into single shot mode. And yeah, so the trigger is there that you can see. Let's bring that voltage up a bit so that we can see it more clearly, and change the time base and slide it along. And look at this, we've got nice clean data. That is pretty slick. That is the data that's now coming out of the optical interface into the, oh, in fact, what would be interesting Where's the other one? Let's grab channel 2. And where are we going to read that from? We're going to take that from take it from here. Sorry about my head getting in the way. Turn on channel 2, turn on run, and what we should be seeing here, so we've got 2 probes in place. One probe, the yellow, channel 1, this is the raw signal that is coming in from the optical interface. Channel 2, the blue one, is now connected to the transistor. So if I very carefully slide this schematic sideways, effectively what we've got is channel 1 connected in, I should be watching what I'm doing there, channel 1 connected in there, and channel 2 connected in there. So channel 1, which is yellow, is showing us the raw data coming from the oscilloscope. I keep saying that for some reason, from the multimeter. Channel 2, which is the blue one, is showing the inverted data, which we are sending to the ESP32. So if I just put that in single mode so that it captures, and you can see there, oh, we've got different, yeah, let's set that into 1 volt mode, and this will show you, and anyway, you get what I mean. You can see there that the blue is the inverted output, the yellow is the uninverted input, and if I reset the 0 point on both of those, you can see that we've got a bit more amplitude on blue than we do on the yellow, which is to be expected. The blue should be switching effectively rail to rail, well, not quite, but it's going to be switching pretty hard between the 2 rails, and the yellow is the data coming in. So, that whole thing would have been so much easier if I had just got the correct pin in the first place. But it did allow us to do something interesting, which was have a look at comparators. I ended up being sent off down this, chasing this squirrel of comparators, and comparators are awesome. So that's the thing that I want to get back to today. And so I'm kind of debating, do I do comparators? Do we do comparators first, or do we do PCB layout? Since I've got all this stuff here on the bench, I'm kind of inclined to play with the comparator. I've already got this connected. And then for the last part of the live stream, I'll mess around in Eagle, and basically what I want to do is turn this into a little PCB with a DB9 connector on it and make it the right size for a D1 Mini, so that we can have an external dongle that plugs into the optical interface, and it gives us Wi-Fi and USB. So yeah, let's play around with comparators. Comparators are fun. Now, where are my notes from when I was drawing those terrible diagrams last time? Comparator. Here we go. These are my, oh, you can't see that. Got to go to overhead. Okay, so these are my, that diagram that I was drawing last week with the comparator circuit. So we've got the in, and this is where I said we made a time machine, and I was told off because we haven't actually made a time machine. All we've done is time shifting. So what we've got is the input coming in here. So this is the data that comes in, and then we use an RC circuit to make a delay on it. And so we've got voltage 1 coming in and voltage 2 coming in, and voltage 1 is the original, voltage 2 is a slightly delayed version. So we've got voltage 1 as the blue one, voltage 2 is the delayed blue, as the delayed red one, and when we've got a rising signal, voltage 1 will be greater than voltage 2. When we've got a falling signal, voltage 1 will be less than voltage 2. So what we're looking for with the comparator is which way around those are. And then the output of the comparator tells us whether we have a rising or a falling signal. And it doesn't, to some extent, it doesn't matter. Well, I'm going to do a whole lot of hand waving here. The values in the RC circuit do need to be tuned to some extent. And it depends on things like how much noise there is in the signal and how much it actually rises and falls relative to the noise. Because you don't want a tiny little voltage spike to cause the comparator to think that you've got a rising signal. You have to filter that out, and the RC circuit filters that out. So where were we? Comparator. Oh yeah, that's right. This is where I was drawing my terrible pseudocode equivalent implementation of the comparator. And what else? Oh yeah, that. This, I crossed it out. But now we're going back to that. So this was the original plan of multimeter, optical interface, RS232, going into an adapter, an ESP, and then going out to USB and Wi-Fi. That is basically what we're going to do today, I think. What's that one? Zigbee? No, that's a different thing. Other notes. I don't even remember what that was from. Now, all right, comparators. So we had this comparator circuit that we were playing with, and it wasn't working, once again, because we had data coming from the wrong place. So the circuit is still here. This is the one that we were playing around with. And I need to do a bit of rejiggering here because I've got the data connected to, let's just move this out of the way. And what else have I got here? Ah, okay, I know what I'm going to do. I'm not even going to use the data at this point because it doesn't even matter. I'm just going to, that's what I actually had this signal generator here for. I'm having a lot of trouble moving stuff around on the bench at the moment. Okay, time for a mental reset. I'm going to unplug that carefully and how are we going to do this? Okay, so most of this circuit is irrelevant right now. All we really care about is this comparator, which is doing, it's that. It's actually two of those, but ignore that. It's a dual comparator, but we're only using one part of it. So over here we have the capacitor and a resistor, which look very, very small. Let's see if we can get some zoomy image. That's about as zoomy imaged as we can get. So just down here, we have a resistor and a capacitor. That is the RC circuit on the input. We have a connection to ground. We have a connection to 3.3 volts. And we have the input. So this orange wire here is this wire right here. It's the in. So the signal that we send in here is going to be checked by that comparator, and it is going to be, we're going to get an output. So I need some jiggery pokery to get all of this on the screen at the same time. All right, so no, I'm just going to set this and then no, lack of preparation. I really should be better organized than this. All right, so I'm going to move this so you've got the signal generator up there. This signal generator is driving a signal out to here. And what have we got here? Mode. channel 1. Okay, I'm going to leave it off for now. It's set. So right now we've got it set to 10 kilohertz. 10.0, you can't really read that, but that's 10 kilohertz. 3 volts peak to peak. It's on a sine wave pattern, and everything else is normal. No offset, no phase change, or anything else like that. So it's just like a simple sine wave that is coming out of this. Now to verify that, let's grab ourselves the Now I'm calling the oscilloscope a multimeter. I need to just like reverse their names. Okay, so I'm going to use the ground off this as the reference. So I'm going to go, well, okay, let's just bypass that whole thing for now. Step 1 is simply to show the signal that is coming out of the function generator. Let's do that. Yep, that's kind of ugly. Run. Turn on channel 1. What have we got going on here? We don't have anything. Do I have this even plugged into channel 1? No, I don't. That would explain it. I've got... There we go. Much better. So now, let's zoom in on that a little bit. So now we've got the sine wave being generated here by the function generator, and all we've got is the output of the function generator going straight into the oscilloscope. And the oscilloscope, as you can see on the screen right there, is displaying that waveform. Now, if I just change amplitude, like I'm going to change from 3 volts amplitude to 2 volts amplitude. Oh, and look, my trigger level has changed. So what you can see is we are simply displaying the waveform. Now imagine that what we have here is a really, really noisy data line. And so instead of being like nice square edged, it's going like crazy. Andy. Thank you. Focus on goal 1 of 3 today. So, all right. Well, at the moment, this is goal 1, which is the comparator. I think this is goal 1. My numbers are, I'm all confused now. So, comparators are cool. This is a really useful thing to have in your toolkit. Now, the thing is that we're not even going to be using the comparator in the circuit for this interface because we don't need it. Now that we've got the data coming off the correct data line, all it takes is one MOSFET and we've got it. That's all we need. But comparators are so cool that it's one of those things that it's really nice to know about and just to have it in your mental toolbox so that if you face this problem in the future, then you can remember, hey, we can solve that with a comparator. And it's actually pretty straightforward. All right, so imagine the situation is we've got this horrible signal that's coming in, and this is actually a nice, neat sine wave, but imagine we had this and we wanted it. Oh, hang on. I'm just getting an error off YouTube telling me that it's not getting data and it's buffering. I don't know what's going on. Hopefully my internet connection is okay. Am I still on? Am I still on the air? Someone wave to me. I don't know if I am. So I'm going to keep talking just as if I am. I don't know. I am. Okay, cool. Thank you. We can hear you. All right. So what we want to do is we want to take this sine wave and we want to turn it into a square wave. We want to be able to detect when the voltage is trending up and just say it's trending up, so it should be on, it should be high. Or the voltage is trending down, so it should be off, like low voltage. So we want to take this meandering signal, which has got nasty rounded edges and things on it and turn it into a sharp square wave so that it's more like a data line. And that is what the magic of comparators will allow us to do. So let's, in fact, what I'm going to do is I'm going to leave channel 1 of the oscilloscope just showing that raw signal that you can see there. And then we can start messing around with the comparator and see if we can get an output from the comparator that will give us something useful. So what we need is a ground reference. First, how am I going to do this? I think I'll connect that on there. I'll connect that on there. All right, so we've got a ground reference. I'm just going to try to get that up on the edge. Move that there. Okay. Now, what's going on? All right, so what we want to do is take the input, so this signal that we are measuring here, this sine wave, we want to send that into the comparator. So I'm going to just sort of jam that jumper wire in there in a totally dodgy way. And I need another, got this whole little box of jumper wires and most of them are rubbish. I should just tip the whole thing in the bin and put some good ones in there, because half of them have had ends cut off and come on, I just want one pin to pin. Surely there is one in here somewhere. A pin to pin jumper which has not had its ends cut off. Here's one. Okay. So this is going to be the output pin. I think it's going to be the output pin. And I'm going to do that. And what is going on there? That's interesting. That's a bizarre looking signal. So, what's going on? Firstly, let us zoom in just a little bit. I probably totally screwed this up. So, this circuit, we had, hang on, I had a diagram here. So we got out A, we got in and in negative and VCC, so we've got 3.3 volts on there. And it's funny how it's influencing the probe. So we've got in, which is connected to that, which goes to ground. All right, so let's, I have a feeling I know what this is. So let's go to offset, where are we? Offset. Take it up to a volt? No, not that much. Take it up 100 millivolts. Nope, that's not it. There is a problem with, this is something that I was going to get to showing, but it's not actually causing this issue. So, I've got something very weird going on here. The bottom of it, I'm just going to do a quick review. So we've got a ground connection going to there, and the input to the comparator is coming to there, which we're measuring off channel 1. We've got the output turned on, we're seeing that. This could be a whole lot of fail going on here. It's one of those situations where I really should have had this better prepared. I thought this was working previously, but maybe not. So, comparator. No. Okay. It is time for me to look at the comments because I've probably got people shouting at me as to what the answer is. In in... No, I can't see it. It's probably something obvious. All right. Station 240, John's home for wayward squirrels. Yes. Speedy squirrels a go. James catching up from at 1.5 speed. All right. Now, because I am probably going to end up wasting a whole lot of your time while I fiddle around with this. The whole point of this was meant to be comparators are awesome, and it's the comparator is not comparating. I'm just going to check my my pinout. So we've got a 10 kilohertz signal. We've got 3 volts peak to peak. We've got oh, hang on. I wonder if that is causing a problem. Let's drop that to 2 volts. No, that wasn't it. Because the comparator is running at 3.3 volts. Sorry, I'm mentally going through what's going on here. So we've got 3.3 volts coming from the ESP32. At least I assume that it is 3.3 volts. And you know what assuming means. It is indeed 3.3 volts. Okay, always best to measure. To measure is to know, as Pancake Legend says. So 3.3 volts into the comparator, we've got ground, we've got in positive going with the capacitor to ground, and we have the resistor. I can't see it. It's not immediately obvious. So what I'm going to do is, what I'm going to do, I think, is move on, because this last thing that I want to do, which was actually going to be thing 2, it's one of those things that usually takes a whole lot more time than you expect, which is doing a bit of PCB layout. So, now, alright, where to go with this? Bring up ye oldie desktopy and get rid of all this. Clear the decks. Get rid of that. Get rid of that. And hardware. So what I've done is, I did actually do 30 seconds of preparation here. What I've done is copied the board files from another project, which was a D1 Mini breakout, and renamed them so that we've at least got a... Oh, Andy said, does the comparator positive feedback signal need a potential divider setting a voltage reference? It does not. So it is measuring, oops. I temporarily have audio, but it's about to go away again. Just give me 1 second. I've got to change my audio input device before it disappears. So, sound preferences, sound preferences. The receiver for this radio mic went flat. That's what happened. Okay, audio is now coming from the webcam. Hopefully that is working. Is that better? You can hear me? I can see audio levels on the screen. Yeah, I've got to chuck that receiver on the charger. Awesome. Now, where are we up to? 10:50. Feels like we're trucking along today. Now, back to the overhead. That's right, this is what I was trying to show you. So this little shield here, that Wemos D1 Mini shield, it's just got some WS2812Bs on it in a little array. And this is, you can see there's a Proto shield there with the piezo module on it. There's a D1 Mini. This is running Tas motor, and this is actually my doorbell. So when there's activity, when the home automation system detects activity at the front door, then it makes a beep and it flashes colours on this little array. Anyway, I designed this shield, when was it? A couple of years ago now, 2017. Nearly 3 years ago. And so anyway, I'll plug it in so it powers up, because when it powers up it beeps and flashes the LEDs. Or it should. Nope. There it goes. But I'm going to leave that unplugged for now. So what I've done is just duplicated the project files for that little LED shield. Oh, Peter says, excellent room reverb. Yeah. I've also got a better mic up here, which Guru of Nothing sent me very, very kindly. He was super generous. In the early days of the live stream, my audio was totally rubbish, and so he sent me this microphone. You can just see the edge of it sticking into the camera view here. So I've got this little shotgun microphone mounted up here, and just recently it stopped getting audio in, so I need to figure out what's going on with that. Alright. I'm doing mental squirrels. Now, this is just a copy of the design for that shield with those LEDs on it. And I just did this because all I want is the shape of it, so that I can just strip the guts out of this project. In fact, let's do this. We're going to go yoink and delete pretty much everything. And delete group, and what do I want? Not going to need any solder jumpers, we'll get rid of those. So delete that group. What do we need? 1 microfarad. Do we need capacitors? This is going to be, no, we don't need 5, don't need 5 volts. So, yeah, go. Alright. So, what are we going to do here? What I need to do basically is recreate. I'll move all of this out of the way. That is what we want to recreate. We want to have a connector for this. We want to take the data into here. We need a MOSFET. We need a a bias resistor on the input. We need a resistor up here so that it goes to, it pulls the data line to high when the transistor is turned off, and that's it, kind of. So let's let's get to it. PCB design in public. Kind of scary. This is not the sort of thing that I would normally do. In fact, let's just get rid of that. So what we should end up with, and if I switch to here, let's rip up let's left those named nets around, we'll get rid of everything. So this will give us just the shell of a project that we can use. Get rid of that, get rid of that, get rid of that. What's that doing there? There was a via for no particular reason. Alright, via or via? I've always said via. I've been told off for that, but it's just habit. It's the way I say it. So, back to the schematic. And what we want to do, let's start by adding the connector from to bring the data in from the come on, you can do it. From the multimeter. Superhouse connectors, that's the library I want. DB9, and I never remember which one. The whole gender thing, I don't know. Okay, so that one is the one. Is that the right one? No, it's the wrong one. I need this one, but it looks like I don't have a model for it. So, alright, we might have to fix that. Now, start with that. And what connections do we need? We want to bring 3.3 volts in there. So this is a bit of an experiment. This is not at all riveting, action-packed TV. If you want action, you'd be much better off watching Eurovision. I don't think I'll ever watch Eurovision. It seems to be what everybody's talking about on Twitter right now. So, what am I doing? Alright, I'm going to grab this schematic and bring it over closer to where I am. I should be able to just do this off the top of my head, but I want to make sure I get these pins correct. So, I'm going to... Now, I like the flow of data to be left to right, top to bottom, like high voltage high up, low voltage down, data comes in on the left, data goes in on the right, or signals, I should say. I'm used to saying data. But let's one, and that's no. Let's unmirror that and just spin it instead. Move. Take it to there. Now, what connections do we want? Which pins are which? Now, we were sending 3.3 volts out on both pins 5, 1, 2, 3, 4, 5, pins 5 and 7. So let's just stick that out there. And where was our ground connection? Ground is, I'm staring at a connection that you can't see, which is unfortunate. No, ground was on 5 and 7. And pin 4 was where we were sending in the 3.3 volts. So let's take that to there, that'll do. So 5 and 7, bring it around here to ground. 5, moved it the wrong way. And what did I just say was our voltage pin? Pin 4, okay. Pin 4. Alright, so this should now give us power going to the optical interface. Then we want to bring data out, and we'll take it into, let's just use a really simple N MOSFET that I have in stock, because I've it's one of those things where you always want to use parts that you already have. What am I looking for? Discrete semi, MOSFET N channel. We'll use a, what do we use? Yeah, let's make it a like a 2N7000 or whatever it is. And the data is coming from, this is the big one, pin 2. Okay, so pin 2. Let's make that a, yes, let's make it a 2N7002. We're going to take our data pin, data coming from pin 2, going to the gate, and we want, what do we want? We want a couple of, where are we? Discrete semi library. This has got to be a terrible thing to be watching. We'll do that there, we'll do that there. Give them values of, say, 10K. That'll do. It's amazing how 90% of all the circuits consist of maybe a dozen parts. The really, really common things like an N MOSFET, some resistors, some capacitors. And then there are some hero parts that do the actual. Let's make this. Also, I'm in two minds about the style. Like, okay, I'm going to do this in two different ways. I'm going to do it in one way and then I'm going to change it. There are two different styles you can use here. What am I doing? What am I doing? I'll do it first and then I'll explain what is going on. Now, if I connect, all right. So let's stick a label on there, because that is going to be the data that we care about. Oh, I'm missing a net. Look at that. Alright, so one thing that I go backwards and forwards on, and I do it different times, different ways, and sometimes I use one style in one part of a schematic and another style in another part of a schematic. So what I'm talking about here is whether you tie all the grounds and power lines together or do them separately. So one thing that breaks my mind is when you've got, see down here we've got these two ground connections. I mean, all of this could be tightened up. Normally I would bring this up so that there is, like my standard way of doing this is that the point here from this junction on this resistor to this junction here, that is one grid step. And normally, and that one is one grid step. So my usual thing, I don't like it when it's like that for some reason. I don't know why, I just don't. I always like to have one grid step so the net is visible. And then you can see all the grounds are lined up. If this was up here, for example, and I looked at that circuit, that would just grind my gears. It would drive me nuts. I would have to grab that and pull it down. So now these are all, I suppose because in my head I think of the Y position of the thing as being like an indication of the voltage level. It's like looking at an oscilloscope. So this is 0 volts. That is the reference down at the bottom that everything should be 0 volts. So I like them all to be lined up. If it's like that, or if it's like that, I can't stand that. So, and similarly here, say 3.3 volts is up here. In fact, let's tighten all of this up. We'll take it down to one grid distance on all of those joints there. And that not being lined up, that I can live with because they are a fair distance apart. And the thing is that if you do that, it looks kind of silly because this just looks like it's reaching for the sky. But I still prefer that. Like, that is visually better because it shows these are the high voltages, these are the low voltages. And we've got data coming from left, coming out pin 2, going to the gate of the transistor, and then here we've got the data coming out, which is going to be the inverted data switched by the transistor when the transistor is on. So when this is high voltage, transistor turns on, and this signal here will go close to 0 volts. When this input signal is low, and this transistor turns off, which means that this data line is going to go high. So basically this is like the world's simplest inverter. And then, okay, so what I was talking about before was different styles. Alright, so here we've got multiple things in parallel. In fact, if you're tightening this up a little bit more, what you would do is bring this along so that there is one grid unit there, one grid unit there. Bring this here, and I think I'll spin this to make those designators readable like that, so that when you're looking at the schematic, things are aligned, you know, the text is horizontal. It's easier to follow what's going on. And then what we could do here, okay, so that is one style. Snapshot that in your brain and imagine what's going on. So the other style, and in order to make this work, I've got to bring these down. Do I? No, I don't. I'm going to add a net across here, net across here. Of course, it means nothing because they're all ground, and then I'm just going to delete these two. And then I'm going to grab this one and bring it down like that. And now what you can see is that this net here, which is all ground, is all tied together. So that is the other style, where you take all the things that go to ground and you just put a ground net and you take everything down to it. So in some ways this is visually better, I think, because it makes it really obvious. We're going to tighten that up. It makes it really obvious that all of these lines, all these signals are the same. Now if you click to highlight, it's going to highlight them anyway. So Some Call It Fun said, I keep stressing that it'll override his original file when he saves. No, hang on, when I save this, I duplicated the design files for that little shield. So what we're editing now is a copy of the files. It's not the original files, so I'm not going to lose it. And it's all in Git anyway. So so Stephen said, wouldn't you need an inverter to convert the RS-232 to TTL? Yes. Yes, that's right. And that's what this will do. So what we're getting coming out of pin 2, which is the RX pin, which is TX from the other end, is the RS-232 signal, except it's not true RS-232. What we're doing here is we're only feeding 3.3 volts into this receiver circuit, which is woefully underpowering it. It's actually meant to be, it's meant to be powered off 12 volts. So the signal that we're going to be getting out of this is not, it's not the RS-232 voltage spec. It is it's a very low level signal, but it is sufficient to switch this transistor, which acts as the inverter, which then gives us the signal we want. So this net here, net 2 in $2, is where we are going to get the data that we will then send into the ESP32. Cabletti, good morning. All right. Stephen W says 10K resistors belong in the hero parts category. Yes. Okay. So what I meant by hero chip, hero part, is if you look at most circuits, I agree. 10K resistors are my hero. I used, it's quite likely that I have, no, I probably have designed circuits that don't have a 10k resistor in them, but I would really have to go looking to find one. So 10k resistors, 1k resistors, little N MOSFETs, 100 nanofarad 0603 capacitors, they're in everything. So, no, what I mean by hero part is, let's, alright, I'm going to find another circuit. So 10k resistor is what I would call a jelly bean part. It's, so that's not my term, it's like just a general thing. Projects, okay, I've got to find one that is a representation of what I mean. Bluetooth serial? I don't even remember what that project is. What is that one? No, not that one. I'm going to find one that I can show you. Alright, this one will do. Share I2C. So, well, this one's got two hero parts, but that's alright. Do you want to load? Yes. Okay, so this is the Permobil wheelchair I2C interface. And so what I mean by hero part is most smallish circuits, like modules or single purpose circuits, will have one part that is the thing that defines the circuit and that dictates everything else around it. And that is the hero part. So in this case, what we've got is this little DS3502, which is an I2C potentiometer. And it's got, you can see these pins here, it's got RH, RW, RL. Those are the equivalent of the 3 pins on a potentiometer. It's got the high, the wiper, and the low. And so as you turn the potentiometer, it moves between the high and the low outputs through this little voltage divider sort of thing, because a potentiometer is a voltage divider. So this is a virtual potentiometer with an I2C interface, and we can use it to generate an analog voltage between the two extremes. Ooh, Andy is paying me to complete goals. Maybe this is the key. if I'm incentivized, then okay, it's like a bug bounty or a goal bounty. Thanks, Andy. So yeah, I won't get into this circuit too much because the specifics of this circuit are not the point. My main point though was that if you look at a typical schematic for a small project, like big ones have many hero parts, but for a small project like this, excuse me, there is the hero part, which is the DS3502, and in this case there are 2 of them, and then all of the other bits are the, oh, good question, Frank, I'll get to that. I'll get to that, squirrel. The other parts are the jelly bean parts. They're the ones that are like resistors and capacitors and all the really common stuff that you sprinkle into a project, and it's all the supporting stuff that makes the hero part able to do its job. So in this case, things like the pull-up resistors on the I2C interface and these little 0 ohm mystery resistors that Frank was just asking about, power indicators, decoupling capacitors, all that stuff. There's a voltage divider here, which I won't get into. I want to do a whole video about this because this stuff is cool. Wheelchair hacking is cool. Ooh, Pancake says 10mm LEDs are the jelly bean parts. Yes. It's like a 10mm LED is half a jelly bean with 2 wires sticking out. Now, mental reset time. Alright, the hero part is the complex thing that makes it all happen. The jelly bean parts are the things that you use to make it work, to support it. So I need some tissues out here. I don't think I have any out here at the moment. So what was I looking for? UT61E. Let's go back to the project that we care about. Oh, now let's just look in here. Is there an example? Okay, here, look at this. Before I switch projects, you can see that this is the DB9 connector that goes out to the wheelchair, and you can see that I've got separate ground symbols here, and I've just pulled everything down to it, and there's a 12 volt symbol here and a 12 volt symbol up here. So that's an example of where I've used the separate style of pulling things down to ground. But if I switch to this one, which we were just playing around with, this is the other style where you have the ground net. And just to make this example complete, joink, and let's remove that. Now, that is actually slightly less obvious what's going on. And this is the reason that I kind of go backwards and forwards between these two styles. If I look at this, what I want to be able to see is this is effectively, well, it's not really a voltage divider, it's a bias. So this resistor is biasing the line high and the transistor is switching it low. So what you can see are the upper and the lower halves, and the lower half, you can see it pulls it down to the ground symbol. The upper half, it pulls it up, but what does it pull it up to? It pulls it up to this net, and then your eye has to go sideways to hit this 3.3 volt. So it's like, I mean, it's quite close. In this case, it's fairly obvious. That circuit, if you looked at it, it's pretty clear what's going on. But let's just revert it to what it was before. But in some ways, that is more clear what's going on, because you can see that this pin is being pulled high or low, because it's all in a vertical line going up to 3 and down to ground. So that portion of the circuit right there is more obvious, but you don't have that visual connection between these two. Anyway, we're not going to solve this problem now. It's just different styles, and I can never decide which one. So I used sometimes I use one, sometimes I use the other. Depends what sort of mood I'm in. Okay. Oh, Cable Tie said, talking of wheelchairs, did you visit the ATSA Independent Living Expo last week? No, I did not. I should have. That would have been interesting. Oh, Ingmar, thanks for coming along. You didn't miss much, apart from me. Oh, I just saw the reminder about 0 ohm resistors. Sorry, I did not explain that. All right, this is a squirrel. We'll go back to the, where are we? We'll get back to this board in a bit. What are we at? 11:17. Yeah, we can do this. I'm just going to take a very quick detour. Save, yes, blah. All right, so why are there 0 ohm resistors in here? The answer is they weren't 0 ohm resistors originally, and I had to change the values because of some stuff that is actually explained here. I've since added this as a note. So what happens, oh, I just realized the size and the agility of this squirrel. This could be a hard one to chase. It's a really interesting subject, but I want to get back to doing this other board. So as it says here, R7 to 10 were originally 22K. Now what happened here is that what I was doing was, so if you imagine these two 0 ohm resistors were originally 22K resistors. And this virtual trim pot, the DS3502, is conceptually a 10K pot. So it's the equivalent of 10K resistance between the high and the low wipe, and the high and the low, and then the wiper moves between it. So what I was trying to do was create a multi-way voltage divider that offsets the bottom and the top position of the pot, so that when the pot is fully, say it was fully towards the high end, you would effectively have 22K at the top, and then you would have 10K plus 22K, so 32K at the bottom. So the voltage here on the wiper would never go full rail to rail. It would only move in a narrow band in the middle, and it couldn't move past the bias of the 22K on one side and the 32K on the other. So it was narrowing the range. And what the purpose behind that was to allow the full resolution of that I2C potentiometer within a narrow band. And it turned out that, well, it worked in terms of if you just watch the signal on this line with nothing else plugged in over here, that was exactly what happened. We got a nice voltage range between those two limits. So instead of going 0 to 3.3 volt or 0 to 12 volts, it would just move within the range in the middle, which was perfect. The problem is what this is connecting to is a wheelchair controller, and the controller itself has a moderately low input impedance, which tends to bias this this line, which is dodgy. It's kind of bad design on the part of the Permobil wheelchair controller. So what was happening was that the bias that was being applied was preventing the voltage divider here from going into the correct part of the range. So what I ended up having to do was put 0 ohm resistors in place on the board, and that way we're effectively, so what we had before was effectively a potentiometer that from top to bottom was 22 plus 10 plus 22 kilo ohms, so 54 kilo ohms, and now it's only 10 kilo ohms, so it applies a harder bias to this line, and then the controller is happy. So we've lost resolution on it. Even that, what I was just trying to give you was like a really trimmed down, simplified version of what's going on there. But I could go on for a long time about that one. I'm not going to, because today, ladies and gentlemen, we are going to be doing this. I want to get this to the point where it may not be polished, but at least it's, you know, a functional design, and I can send it off for fabrication sometime after the live stream. All right. So reorient time. All right. Now we've got a whole bunch of notes in here. There's lots of stuff to clean up in this schematic. Let's just change this. D1 Mini UT61E multimeter adapter. Doesn't fit. Let's get rid of that. And I don't know, what do we call this? UT61E Wi-Fi. That'll do. Change that. UT. So what you're seeing right now is the reason that I have so many broken URLs on yeah, so this is when I did this other thing, 2017. So many broken URLs on my projects is that when I do these designs, what is the date today? Is it 23rd? Where's the date? 23rd, yes. I just make up an SKU, like what is the product code going to be for this thing, and then I just make it the URL, and then I don't actually create the page for the project. So I get people all the time who contact me saying, I've seen the design on GitHub and the link is broken. Yes, I'm sorry. All right. Now, yeah, so just going back to that 0 ohm resistor thing. Yeah, there are many reasons for using 0 ohm resistors. In this case, it's because I didn't want to revise the PCB. I wanted to be able to, in future, assemble the boards without those 22k ohm resistors in place, and just effectively I wanted to tie those two nets together, and a 0 ohm resistor allows me to do that. But one of the reasons for also not modifying the PCB is I want to revisit that whole thing, because not having the full range of basically we're losing resolution by not squeezing the voltage into the middle of the range. I want to come back to that and revisit that, and maybe have like a buffer circuit, so that what I can do is put the 22k ohm resistors back in place, which will give me the voltage range I want, and then have that voltage go into a buffer that then drives the wheelchair controller. And that way I don't have to change my PCB. But if I add the buffer, I do. Anyway, I want to experiment with it in future, maybe with lower value resistors, so we get some kind of a compromise. Alright, now, let's just do a quick review of this to make sure. What have we got? So we have pin 7. Let me grab my little highlighter-y tool. So we've got pins 5 and 7 connected to ground. According to my piece of paper, 5 and 7 were connected to ground. Common, yes. Then we have pin 4 going to 3.3 volts. Is that correct? 1, 2, 3, 4. Yes, that's what we had going to 3 volts. I'm just verifying against the actual device here. So we've got ground, yep, then we've got 3.3 volts, and then we're skipping pin 3 because that is not the TX pin, it's the RX pin. And then we've got, well, it depends on your perspective, doesn't it? And then we've got pin 2 as the place the data comes from. Alright, unless someone is screaming at me and saying, no, you've made a mistake, I think that circuit is what we want. Have I got the one thing I really should do on the footprint that I use for these MOSFETs is add no, I won't do it now. I was just going to add labels for gate, drain and source, but I won't do it. So now, next thing is, where is this data going to go? We will need to connect this into, now do I still have, no I don't. What pin were we taking it into? Pin 16 it looks like. So GPIO 16. Now what is GPIO 16 on, where is it? 15, there it is. GPIO 16, which is D0 on a D1 Mini. So you can tell that this was done a few years ago because my my style has changed since then. In fact, I'm going to fix that. Now when I'm doing, I think it's because Eagle didn't have this style of label originally. It only had the labels that, you know, hang off on the sit on the tops of the nets, and I was quite happy when they brought in this style of little flag label sort of thing. So let's get rid of these other labels and we'll switch to the flag style of it. I don't know what they're called. The little panel labels. So, all right. Now let's just move these in a bit. Move, move, and then that makes that rather ugly, still rather ugly. 10K pull down, no, we don't want that. These labels are wrong because those are for the other shield that we stole this design from. So let's neaten this up a little bit. Oops. Ah, still ugly. Okay, let's get back to that. Alright, so I am going to rename this net. Now this is something else that the way I've done this has kind of changed over time. I've gone through different ways of doing naming of nets, and in particular the data lines that come off microcontrollers. So what you can see here is these nets are all named for the pin that is on the D1 Mini, and you can see it's got A0, D0, D5, D6, etc. And then I've put labels over on the other side that are the actual ESP8266 pins. So GPIO 16, and hang on, what am I looking for? Is it GPIO 16? Yes, it is GPIO 16. Is where we are currently taking in that data. In fact, let's go back to here and just confirm this. Cable Tie says, I reckon uses for 0 ohms could be a topic for a whole live stream. Yeah, I've used them for a few different purposes. I saw the one talking about using it as an igniter. Yeah, basically a fuse. A 1/10 of a watt fuse, or whatever an 0603 resistor is rated to. So while we're waiting for this to open, it's drink time. Okay, cool. So, hang on, I've got to move this off the screen so you can't see it, just in case I'm about to reveal something in my config file. I'm lucky I did, because it's got my Wi-Fi username and password in here. Alright, pins. The receive pin coming from the multimeter is pin 16. Yes. Okay. So, which is GPIO 16 D0. So, now, this is where the question of naming convention comes in. So, and also the other thing I'm going to do is drag this right out here and give it a different name. Now, there are really 3 pieces of information that we want to encapsulate in the naming of this net. In the past, I have often done it by having it as just the pin signal name, like GPIO 16. So one way to do this would be to just call this like IO16. And then at the other end, in fact, I'm going to do this. I'm going to make that IO16, and I'm going to name this one to IO16 and demonstrate the issue. Now these 2 parts of the circuit could be on different sheets. They may not even be anywhere near each other in terms of proximity on the schematic. Because what often happens is you end up with, well, what happens to me anyway, if I've got a large project and it might have 6 or 8 or 10 sheets in the schematic, there will often be one sheet on the schematic that's got the microcontroller and its basic supporting stuff. Things like USB interface, if there is one, programming, like other programming header, ICSP, reset management, all of the things that are like core to the microcontroller and that are not necessarily specific to the circuit in any way at all. In fact, a lot of my projects have a sheet that is very similar. It's like the ESP32 and all its supporting stuff. And then there'll be another sheet in the schematic, which is the parts of the circuit that are specific to what you're trying to do with that project. So what you find is that there might be a part where you've got a whole bunch of pins like this coming off a microcontroller. In this case it's a header, but it could just be the actual microcontroller on the board. And you've got all of these nets, and they'll be labeled things like IO16, IO12, but you've got no idea what that does. At the other part, in some other part of the circuit, you will have this function and it will say IO16. And so from the perspective of the other part of the circuit, you know what it connects to. But from this part of the circuit, you've got no idea what that connects to or what the purpose is of that particular net. So what I did for a while was, so I'm getting to the point where I'll show you what I actually do now. So what I did for a while was I would name the net after the purpose. So in this case, I'm going to say this is, what do we call it? RX data. So we're going to receive data from something. Okay, so now if we're looking at this part of the circuit and we've got the microcontroller here, and the pin will typically be labeled in the schematic, so it'll say GPIO16. We can look at that and say GPIO16 is RX data, it's receiving data. But then you've got the opposite problem, that you're over here in this part of the circuit and you're looking at this and you're saying, okay, we've got this data that comes in here, we're inverting it, it goes somewhere, and this net is called RX data. What the hell is RX data? Like, where does it go? What does that mean? If you're looking this up, and say you're working on the firmware and you want to know, what pin is this? So if you go and look over here, then of course you can match it up. It's that one level of abstraction. So the problem is, should it be representing the level of abstraction which is the purpose of it, or should it be representing the pin? And my answer is yes, it should do both. So more commonly now, what I do is it'll be something, and it makes your net names really long and unwieldy, but I will typically do something like this. And normally what I do is not have a space or like an underscore. So it'll be pin identifier, or really IO identifier, whatever that happens to be. And the important thing is how you would address it in the software, because the real issue where this becomes an issue is you're sitting down to write the firmware for this thing and you're looking up, okay, I need to address that bit of information, that bit of IO, what pin am I using? So this encapsulates everything. So now we can look at this and see from this point of view, yeah, it's IO16 and it is connected to, it is RX data. It's where we're going to receive the data. And up here we can see, yes, this is the data and it is connected to pin 16. So you end up with kind of these longish net names, and the real thing here of course is this is actually D0 on a D1 Mini. Now in this case, I'm not sure if I care. If you wanted to be, right, D1 projects are often, what do we do? We'll just make this D0 IO16. Now, this is also perfectly legitimate, and in many cases this is what I would do. In fact, I think for today this is how I'm going to leave it, because what this represents, now if we come down here, D0 is not represented here anywhere else. We've actually got no way of knowing that on a WeMOS D1 Mini this is the pin that it considers to be D0. So we want to know that it's D0, we want to know that it's GPIO16, and we want to know the purpose, which is RX data. So yeah, you can end up with a schematic that has huge labels everywhere, but over time I've kind of moved more towards this sort of verbose way of naming things, just because it makes it so much more self-explanatory. So if you come back a year from now or a couple of years from now and you're messing around in the firmware or whatever, and you've got part of the circuit open and you look at this, that is super obvious what is going on. You know that you can address this as IO16. This is connected to pin IO16 on the processor. And you know what its purpose is. And it's obvious there, and it's obvious there. So, Gerald said, self-documenting. Yes. Now, what are we up to? 11:40, and we haven't started any routing. What I was really hoping to do was get to the point of having some tracks routed today. So let's do that. We're not going to get this polished because even with something as simple as this, I could sit here fiddling with it for hours after it passes ERC and DRC, just, you know, getting the logo where I want it to be and making sure the labels on all the pins are neat and putting headers and boxes around things in the schematic. So at the moment this schematic is a bit of a mess, and it's still got, you know, these sorts of comments on here. So that cleanup can take a lot of time. So let's just do a very quick thing on here. A0, D0. No, we don't care about any of that. Let's just say D0 data from multimeter. That's the other thing I often do is on the schematic I'll have a chunk of text and I explicitly list all of the pins on the microcontroller and what the purpose is for each one. And it almost becomes a copy and paste into your software project, because what you can do is if you've got a list of all of the pins here, you go into here, copy it, you paste it into the config file for your project, and then, you know, a bit of munging around, and you just do like a hash define, you know, IO16, hash define data in IO16, you know, something like that. You can take it from the description here. So the pin definition here, and I do that with I2C addresses as well. So if you look at the primary, if you look at the schematic page for the microcontroller, or like the brain of a project, you should be able to look at it and see a list of all of the pins, what they're used for, all of the I2C addresses, what they're used for. I don't like having to go digging through pages and pages of a schematic to find a particular part to look up its I2C address. I will typically list it in two places, so I have it both at the part in the schematic and in an explicit list of all the I2C addresses that are used in the project. That will be on the microcontroller page of the schematic. Anyway, a lot of the stuff I'm talking about now isn't even relevant in this, because this is like the world's simplest schematic. It's one connector, two resistors, and a transistor. That's it, apart from the D1 header. So let's do some moving around. Now, where's the, I want to turn on, I don't even know if this part has a, where are we? TDocu, that's what we want. Yes, it is. There we go. It's got a, in the docu layer, it's got an orientation marker. Now, which way around? I've got a D1 Mini here, so I can just do a quick sanity check. So the USB connector comes off the same end as the reset switch, which is where the notch is down here. So let's just do some really gross level manipulation, moving things around, and do I have all the layers I need? Yes, I do. And for now, what I'm going to do is just take this and move it. What's my grid set to? 1 millimeter. That's all right. And I'm just going to yoink it right up here, make it long, and well, that sucks. Maybe I should put it on the side. I've got to think about where the cables are going to come out. So what I had in mind here was making an adapter that would have... Alright, I've got to grab a connector. There's some connectors around here somewhere. Hang on. Camera change time. Looking at this now in the board layout. Sorry, I'm kind of shouting from a distance. It's not fitting the way that I thought it would. So in my head, I had one thing in mind, but I think we're going to have to do something slightly different. Now, I've got the connector, got the D1 Mini, go to the overhead camera, over hideous, and, oh, sorry, I've just got to switch this to where I can see it. Alright, so, what I had in mind, that's better, I've had that buzzing of the scope in the background the whole time. Alright, so, D1 Mini, oriented like this. Connector, oriented like that. This is what I had in mind. So what I thought we would do is make a little PCB that goes under the D1 Mini, or maybe over. I'm not sure of which way around. Basically a carrier board. So what I want is the PCB to come off the connector here, for the D1 Mini to go onto it, either that way around or that way around. And so like an over-mounted shield or an under-mounted shield. And that has USB coming in this side and the connection here going out to the multimeter. Now it's kind of unfortunate that the antenna is in the middle here right behind the connector, but yeah, I don't care. I'm not going for long range with this. In fact, it's probably going to be plugged into USB. So what you can see though is the connector is a little bit wider than the D1 Mini. In my head, the width of this connector was about the same, and it's kind of wider. So we can make the carrier wider, or, sorry, back here, we can mount it sideways like this. But what this means is we would have the cable coming in here from the optical interface, and we'd have the USB cable coming in here. So we've got them at right angles to each other, which kind of sucks. I much prefer the idea of having them in line like that. Don't know how other people feel about that. So, what I was thinking, back to the desktop, so I could either put this here, in which case it's smaller, or I can put it here, in which case I'm going to have to make the whole thing a bit wider to account for the size of this connector. I'm inclined to do it this way. Oh, Jordan said both cables should come out the same side. I think that could be tricky. That could be really tricky. Unless the D1 Mini was put on the opposite side. But I think it could also be really awkward, because normally you want the cables to be in line. So you've got the cable coming from one device through the adapter and then the other cable coming out the other side. So if we spun this around, so USB is at the bottom. I was going to point at the screen, you can't see where I'm pointing. So USB, I'm just going to drop this. The USB connector is down here. The cable comes out the bottom there. If this was mounted this way somehow, then both of them would be in line. But I don't really like that idea. So I am inclined to stick it somewhere like this. And bring this down to, yeah, about there. That'll do. Make it all a bit wider. Let's just stick this over here. Now, the other thing I'm thinking about is over versus under for the D1 Mini, and whether whether I want the D1 Mini mounted under the PCB. I kind of want this all inverted. So yeah, Aaron said feels more like an inline adapter to me. And Gerald said, could you use a room module? Yes, I could. Yeah, and Frank pointed out side is best for the RF signal. Yes, it is, but I don't think it's going to make a really big difference. I'm not going to be pushing the extremes of range with this. This is just going to be something where it's got to connect from here on the bench to my general Wi-Fi, which has excellent coverage, and also the part is that it's the part that it's backing onto is mostly plastic. It's just the connector, and all it's got is a few wires going through it and the plastic body. So if there's a few millimeters gap there, I think the Wi-Fi range is going to be fine. Yeah, Stephen said under the D1 no ground port to help RF. Yep, that is a very good idea. So that would be through this region right there. That is approximately where the antenna is. So no ground port under there. And the thing is that it's not going to be, the two things aren't going to be smacked right up against each other anyway. There's going to be a bit of space. I think, oh, and vertically we've got a fair bit of space too. And the other thing is the question of, do I put connectors in there, or does this just go straight onto the PCB? All right, in the interests of making progress, let's, I'm just going to, instead of talking about this, I'm just going to start doing some stuff and kind of talk through it as I'm doing it. So I've just locked those two connectors in place because I want to make sure that the pin headers, what I do not want to happen is what happened with the very first Arduino, where the header was bumped off the grid, and then we've been stuck with misaligned pin headers on Arduinos ever since. So that's what happens when you're working late at night and rushing to get a design off for fab. You can make a mistake that will have ramifications for millions of people for decades to come. So, how big do we need to make it? Just a little bit bigger, I think, than, oh, and there's that. Do I bring that? Because of this weird shape, I'm just doing a bit of a mental debate about what to do about widening it. Let's bring it to about there. And I would kind of like to center, I've got to change my, change the bend mode. I'll bring that up to there, come on, and that up to there. Okay, we got there. Now, I'm going to do something that might seem strange to do at this early stage, but I found that this is something that really helps a lot. I'm going to push it to Fusion 360, particularly dealing with this sort of thing where you've got multiple parts and you just try to work out the orientation around them. Where are we? Superhouse module, so I'll do. Let's push to there. There's no connector on the DB9, which sucks. I'm going to have to fix that, because if I had that in place, it would be a big help for this particular visualization. What I like to do as I'm working on boards like this is, even in the early stages, and probably actually particularly in the early stages when I'm working out the general orientation, how things are going to fit together, I like to have it all synced to Fusion, because then I can just have this 3D visualization. And that's really one of the advantages of having the big screen setup that I have. So what I usually do is I'll have the schematic and the PCB open, And I will also have Fusion open so that I can see the 3D view. Come on. Push to Fusion. You can do it. Sync. If you sink, you must drink. Maybe that should be the drinking game. The Superhouse drinking game. Every time you sink, you drink. Now, Fusion. Now, cable tie said, what's that cut out for? Gerald 42 is spot on correct, the reset button. Yeah, so, Aaron said, do you have to use an RS232 connector? The reason I'm doing that is this is kind of an interim thing. I want to make a plug-in adapter that is going to work with the existing optical interface. So I want to be able to take a multimeter and grab the standard optical interface and just plug it in and plug this device in, and boom, you've got Wi-Fi and USB on your multimeter. So I don't want to have to cut off the cable. I mean, it's easy to do. I could just put pads on the end of the PCB here and not put on a connector, and then you get the optical interface, cut the connector off it, strip the wires and solder them on, and then you could even, you know, use some glue line heat shrink or something and shrink the whole thing so that you've got this on the end of the cable. But for this first iteration, I'm just going to make it so that it's socketed. Yeah, so Aaron said, if this is for your desktop, maybe using ESP32 as a BLE HID device would be nice. Interesting. You could make it a virtual keyboard that types out the values coming from the multimeter. Cool. Yes. Aaron said, is there an ESP32 with a D1 Mini form factor with like-for-like pin layout? Yes, there is. It's called the Mini Kit ESP32, but it's wider because there are far more I/O pins. So the I've got some around. Anyway, I won't go looking. So we're still waiting for Fusion to open. So so what they did was, let me just switch while we're waiting for Fusion to open. Switch back to overhead. Because you've got, so the way the ESP32 mini kit works, it is 0.2 of an inch wider because they've doubled up the headers. So it's got headers that are the equivalent of a normal D1 mini, and then it's got a second row of headers beside them, you know, one step out, 0.1 inch out on each side, which has got a whole lot of extra I/O. And the PCB is proportionally larger. It's just a little bit wider. So basically it means that you can use D1 mini shields and they plug in because they fit with the inner row of headers, but you can also use all of the extra headers if you want to design something that interfaces with it. Oh hey! Looks like Fusion has almost finished opening. So let's go to, this is all stuff because I've been working on my pick and place machine. I've been designing and printing odds and ends for that. Some of you might have seen the posts on Twitter and Facebook about that. So the pick and place machine is working really well now. The vision is working. What am I looking for? I'm looking for Superhouse. Oh, maybe it's pinned. Superhouse modules. Okay. And it'll be down near the bottom. UT61E Wi-Fi. Okie dokie. Of course, once Fusion is opened, that took a very long time to open, but once it's open, of course, it's not nearly that painful. So this is what we've got so far, minus the connector. Now, I would love to get the, I want to get a model for the, yeah, because I've turned off those layers, we can't see them in Eagle, but I've got to fix all of that. And this is actually something that is really beneficial to having this open in Fusion as well, and constantly referring to it while I'm doing the board layout, and then I just periodically resync it. Being able to see this visually, I find really helpful. And now let's library. I'm going to do something really nasty for now, I think. I'm going to what am I doing? Libraries? No, I don't want that. I want Open Library Manager. Sorry, my brain was in a totally different place. Alright, connectors. I want to edit that one. And what have we got? DB9, we've got two different versions. One of them has a model, the other one doesn't. So where did that model come from? This is probably, what are we at? We're already at 12 o'clock. And I have kind of a hard limit today because I have to pick up my wife from the railway station. She's coming in on a train and I need to be there. So I've got a little bit longer, but not a lot longer. And then I absolutely have to leave. So we've got the 3D model, as you can see there, on the female version. We don't have a 3D model on the male version. So can I fix this right now? No. It's going to take longer than we've got to fix that. So what I'm going to do is I'm going to totally fudge this. This is a horrible, nasty thing that I'm going to do only for the purposes of this live stream, and then I'm going to fix it. So we've got this connector right here. I'm going to put that in temporarily because the male version has the model, the female version doesn't. Or the plug in the socket. I don't like those terms. Anyway, let's not get into that. So now we have this connector, which does have a model, and I'm going to move this one aside and put this one in as a stand-in for it. Save that and we will resync it. Retrieving, and at least then, oh, and no, before I do that, I'm going to change, oops, let's just do this. So what we've got here is there are so many little fiddly things here that are a problem because of this. I'm basing this off an old design. So what I was going to do was replace this with a version which has headers on the model. So will I? I'm doing all these. Alright, I'm going to bring it in once again as a separate connector. What do we want? We want an 8-pin connector. M08, and I want an 8 with a socket. I'm going to put that one there, and put that one there. Oh, in fact, what I should do is rotate and mirror that one so that it's the same. Now, and the reason, I don't even know which one is which, but it doesn't really matter for now. I'm just doing this once again as a representation. Now, what you can see here is the origin for this connector. Now let's get rid of that. The origin point, the 0 coordinate point for this connector, is in the center of pin 1. The origin point for this connector is in the mechanical center of the connector. And that means I can't just do a direct substitution unless I change that offset. So, alright, I'm just going to, this is so dodgy, I'm just going to overlay that on that, overlay that on that, and overlay that there. Alright, so this is totally faking it. It's not even accurately aligned. I'm going to push it, But what this is going to do is give us a very quick visual representation of how the different things fit together. And then we're going to even pull in a D1 Mini into the model and see how it all fits. Alright. Yeah, so Aaron said, add the male 3D model to the female footprint as a temporary measure. Yeah. Please try again. Oh, I don't know why, but this thing has been happening recently. Don't save. I think it's just a change in Fusion 360 recently, where if you try to push while it is open, I mean, it's kind of a sensible thing, but it's just annoying because of the way I use the workflow. If you have the project open in Fusion 360 and you've changed something, but you haven't saved it, when you try to push from Eagle, it comes up with that weird HTTP error. It's totally unintuitive. It doesn't tell you what the problem is. It just says, you know, whatever that thing was on the screen a minute ago, unable to push HTTP error 0. Like, error 0 means nothing. But what it means is, see, now it's successfully pushed. So what it's preventing you from doing is updating the project while it is being edited in here. And it's preventing like a race condition on who's going to save first or last. Oh look, there we go. So now we can see the connector. It's the wrong connector, and the position of these connectors isn't spot on because I didn't do the correction. But that's approximately, you know, what the thing is going to look like. Now, where do I have a D1 Mini? Do I have one somewhere? I'm sure I do in some project. What can I do? Where? Is there a resources? I can't. It's a while since I've. Yeah, maybe in resources? Nope. It's got a Raspberry Pi in it and nothing else. I'm sure I've had a D1 Mini in some project. Don't know. What about in miscellaneous parts? This has got models for, as you can see, just all sorts of random things. But no D1 Mini. I was just going to bring a D1 Mini into this model and sit it here on top of the headers so that we can see how everything fits together. I think what I need to do is do a little bit more homework, a bit more preparation, and next week we can come back and finish the routing on it. Because, where are we at? 12:06. Oh, stop that. Okay. And move. So the routing on this is going to be incredibly simple. There's really not much to it. I can do the basic placement right now. Like that. That's basically it. Well, that one, let's spin it around there. Yeah, that's probably adequate placement. Although I want to get, oh no, that's ground, that's alright. Hang on, why don't we have, what net do I have on that polygon? That's ground. On there, what's this one? That's ground as well. So why, oh, I know why, it's because of, yeah, it's because I've got these other stupid headers in here. I've got the temporary ones in there. If I do that, it'll make the ground net go away. Okay. So, what do we have? We've got data going to there. We've got 3.3 volts that needs to go there and there. And we've got that connection there, and that one there. It's like the simplest thing in the world to route. But I don't want to do that just yet because I want to be able to represent this properly with the models for the parts and the headers and all of that sort of thing. And so what I think I need to do is before next week, I will fix the 3D model on the on that DB9 connector. And these are in your RF keep out zone. Thanks, Stephen. That's a very good point. Let's do that at least. What do we do? We'll put in a rectangle in. I can never remember. Is it restrict or keep out? I think it's restrict. So let's do T restrict and stick a polygon in right there. Does that do it? Yes, it does. Alright, and then we'll do another one in B restrict. And we'll stick another one right there. And now, when we do the rat's nest and it does all the ground pause, it's going to be a bit of a pain routing around that, but oh well, that's the way it is. So we probably want that a bit bigger also. So this is where having the model with the, like once we, okay, let's push that. I'm going to go push to Fusion. I wonder if it'll work this time because I haven't changed anything in the Fusion 360 version, but I do have it open. Peter, how much sponsorship to forget to collect Mrs. Superhouse? No. Yeah, I am not going to forget. And I am going to wrap it up pretty much after this. So, next week, if I do a little bit of preparation for next week, I'll set up the 3D models, and then I'm also thinking about how to mount this. I'm still going over in my head whether I want the D1 Mini to be... Now the thing is that normally with the D1 Mini, what you would do is put... Okay, that's been pushed. Nice. I'm just going to bring this up and then do a very quick wrap up. Where are we? Superhouse modules. Oh, I shouldn't have closed that. I should have just done a refresh. Would have been quicker. Alright, now because I moved those pin headers out sideways off the PCB, it looks a bit ridiculous, but anyway, you can now see the keep out area there. That's where the copper has not been poured in that section, and it should be on the bottom as well. Should be a bit bigger. I might take it up a bit higher, bring it down a bit lower. But once there is a D1 Mini in there in the model, we'll be able to see how that aligns with the antenna as well. Okay, now, back to this. So, what the usual way of doing this, in fact, if I grab this, this is a perfect example. This is the D1 Mini with the little LED shield on it. I can feel a sneeze coming on. I've got to try to resist it. And this is how I would normally set up a D1 Mini. I would put the socket on the top of the D1 Mini. So you can see it's aligned with the USB at the bottom. The reset button is on the bottom left corner. I put sockets on it, and then the shields go in on top. Now I know other people do different things, but I'm just in the habit of doing it this way because that's the way Arduino works. And I kind of think of this as being like a tiny size Arduino. And then shields go on by having pin headers underneath. Once again, the notch is on the left to align with the reset, and it goes down and it just sits on top like that. So that's a classic shield sort of arrangement. Now, the way this project is currently set up, with the way we've got it right now in Eagle, it's kind of backwards because we've got the carrier board on the bottom with the D1 Mini on top, which means we can either solder pins or something going down from the D1 Mini, or we can just flip the whole thing. So mount the D1 Mini upside down and have pins coming up this way, like that from the carrier. So the PCB that we've got at the moment, I am really tempted to flip 180 degrees so that we have it like this, with pins coming up from that, and then the D1 Mini mounts upside down on top of it with sockets, like that. I'm still undecided about that. Before we go all that much further, I'm going to have a think about that. And yeah, our cable tie said you could update the D1 Mini header footprint to include the keep out. Yeah, this isn't actually a, where are we, desktop? This footprint here is just two headers. It's not a unified footprint in Eagle for the D1 Mini with all of the geometry and everything. So if I was making a footprint for the D1 Mini specifically, then yes, I could include that. Put the keep out and things in there. Or the restrict rather. So, don't know whether you follow what I was talking about with where that is going, but I'm thinking of just reversing this whole thing. Mirror that PCB so that it flips over and the reset button is on the right, and mount the D1 Mini upside down on top of it so that it's kind of like the other way of looking at it is being mounted upside down. So you could think of it as being like a shield. So if I oriented it like this, you know, the notch would be on the other side, but you could think of it as being a shield where the parts are on the bottom and there are no parts on the top, and it plugs down onto the top of the D1 Mini. So the D1 Mini in its normal orientation would have the sockets on it, and then there'd be pins underneath here that go down into it. Wouldn't it be easier to just flip the connector? Yes. Or would it? Anyway, I don't know. I'm going to have to sit and ponder this for a little bit. Maybe if I do the homework of getting the parts prepared, then, and I'll make sure that I've got a D1 Mini model in Fusion 360 as well. Next week what we can do is we can have all of the things in here. We'll have the model of the D1 Mini, and we'll have the proper headers and everything, and then we can see how it fits together. Now, one thing that you'll see here, I'll just finish off with this, I think, before I really do have to go. You look at the height of this connector, and then if you add in, I think it's, what, 2.54 millimeters is the thickness of the plastic on the pin header. So if you had a pin header on the D1 Mini, and then you've got the PCB, it actually comes up above the height of this connector here, of the DB9. I wanted to keep the whole thing compact and flat, so putting sockets in here, putting pins and sockets, maybe we don't want to do that anyway. Maybe what I want to do is just put a pin header in there and solder it on to both the D1 Mini and the carrier so that they're just permanently attached and you can't ever remove them, because that would make the whole thing very low profile. So yeah, this is the thing, is when I'm working on projects like this seems like the simplest project ever. It's one connector, one transistor, and two resistors, and you know, plugging into a D1 Mini. It is so simple, and yet little decisions like this about the orientation and how it all fits together, I could mess around with this for hours just trying to figure out the best way to do this. So I think it's time to wrap up. I've got to go. I need to make sure that I am definitely not late for making it to the railway station, and I need to do some homework for next week. Did I cover everything? Okay, the three things. We got the data off. We've messed around with this, haven't completed it. We tried to do a comparator demo. The demo failed. Yep. Aaron said, suppose if you're doing that, don't use D1 Mini, just use ESP module directly on your board with USB, etc. Yeah, that would be possible, but it's more work because putting USB on it, and the thing is that the D1 Mini, you can get these for like $4 or whatever. And this project, it's not like, this is not a volume project. I'm going to make one for myself, and I bet maybe 2 other people will ever care enough to want one of these. I'm kind of doing it just for the exercise of learning about all of this sort of stuff. So it's not worth optimizing. I'd rather just make a simple carrier board, D1 Mini, and then we've got USB taken care of and don't have to care about any of the other stuff. So I'm going to go. Thanks for hanging in here with me, and we will talk again soon. I hope you have a fantastic weekend. Pancake Legend, yes, you have a great day as well. Yeah, Stephen W. said, sometimes it's not worth reinventing the wheel. Yeah, it's a question of what is it, where is it better to put the effort in? Is it worth a complex board when I'm going to build like 2 of them, or a simple board that is not as optimized? And in this case, I'm going to go for the less optimized board. All right. Okay. Thank you very much. I've got a... How do I end this live stream? That's right. I hit the end button. Have a great weekend, and I will talk to you all soon. And go and make something awesome. Bye.